Get it? It's a joke. So I'm working on the video for brushless motors, and that'll come along later. In the meantime, I thought maybe I would answer some questions. And so here are 8 questions that you have sent in. Here are all of the questions with time codes. That way, if you want to jump to one, it's pretty easy to, or sit back, relax, and listen to them all. I'll also put up links and maybe additional notes of anything I can think of at AddOhms.com/QA02. With that, let's get on to the first question. Rakesh asks, why does the direction of the current change in an AC source? Well, this question actually comes up about once a month, and I just picked this one for the screenshot. And so one thing to note is that AC can mean a lot of different things. Now, I think in that video, the assumption is that we're talking about mains AC. And so that's like the kind of AC you find in your house. Now, part of where some of these questions come from is why do we use AC when most of the things in our home are DC? And it's really just a question of what infrastructure does a certain country have? Most countries with electricity use AC. And if you want to know why, then do a search for something called the War of the Currents, and it'll explain, well, maybe, you'll learn why AC ended up being used today. And so it's not entirely because one is better than the other, it's just what was picked a very long time ago, and now all these infrastructures in place for AC. Okay, so now on this question, why does the current change direction? First, go and watch the video I recently released on motors, number 20. Now it is a DC motor, but the principle of how the motor works is what I want to use here. In a motor, you have a magnetic field that is driven by current going through a coil. And then when that magnetic field is created, the motor turns in the direction of the field. Well, generators work in the opposite way. So with a generator, you spin the generator around, which generates a magnetic field, and then that magnetic field actually induces current onto coils. And so that's how you actually get current flow out of a generator. Now, it's not creating energy, well, because you can't create energy, but it is what creates the current flow. And so what that means is, depending on how the generator is designed, then the magnetic field and the rate at which it expands and collapses becomes the frequency of the AC signal. And then the fact that it reverses direction is just how the motor is wired up. And so when it comes down to it, the AC waveform, or why the voltage goes up in one direction or current goes in a direction, is due to the way that the generator is designed. In the case of why we use AC, well, that's sort of a matter of history. All right, the next question comes from Akesh and Cody, and it's pretty common related to what uses AC and DC and why. And so, for example, Cody was asking if you put DC into an AC light bulb, what's going to happen? So for an incandescent bulb with a tungsten filament, the kind that's kind of getting phased out now, it'll actually work. But because if you put 120 volts DC on it, it's not really designed to be that hot all the time, and so it'll burn out pretty quickly. Now, for something like a fluorescent bulb, or maybe even an LED bulb, those have a lot of electronics built into them that expect a AC signal. And so, not really sure what would happen, but I don't think you want to be around when you try it. Now, if we go to appliances in the home, this is a little bit more interesting because appliances like, say, a clothes washing machine to wash your clothes, there's a bunch of motors inside, and those are motors basically run directly off of the AC coming out of the wall. The way that the really cheap ones get controlled is that it's a mechanical timer that literally just turns on relays and switches and solenoids. And so from an engineering perspective, I find it fascinating because they do a lot of complex things, but with really simple control. But the idea there is that the motors are designed to be controlled by or powered by an AC signal. Newer appliances, some which might be called, which might hear called cheap, I'm sorry, not cheap. The newer ones, the high efficiency is the word I'm looking for. So if you hear like it's a high efficiency appliance, usually what that means is there is a variable frequency drive, which takes the AC from the wall and converts it into something else to control the power output of a motor. And so for example, like on a refrigerator, maybe the compressor doesn't run at full power as the target temperature is reached. And so what's really cool about these VFDs, the variable frequency drives, they typically take an AC signal in, convert it into DC, and then convert it back to AC at a different frequency. And so that's actually something I want to cover later on down the road, because I just think that's a really cool method, and it's used so much today. Electric cars, solar panels, refrigerators. So in general, appliances primarily run on AC. Now they may have a DC controller, in which case it brings us to what about all the DC stuff in your house? Your TV, modern TV like an LCD, a computer, those kinds of devices, they're all digital devices that run on DC. Well, you know those little bricks or blocks that come with them? Those are AC to DC converters. And so basically what you're doing is you're taking the wall voltage, converting it into DC, and then using regulators, like we talked about in number 18 and 19, into DC voltages. So that's what's going on there. And that's definitely something I want to cover more in the future with a diode bridge or rectifier bridge and transformers, and that's actually a cool circuit to kind of take a look at. Okay, so this is a little bit longer of a question, so I'm going to summarize it. Rain is wanting to know if analog is more precise than digital, why is digital considered better for transmitting data? I think this is a great question because it's the difference between theory and practice. If you could create a pure analog waveform and transmit it without adding any noise, then you could get a lot more information transmitted by just using the continuous changing voltages of an analog waveform. But there's going to be a limit to the amount of precision that you can adjust a voltage to, detect the voltage, and then any kind of noise that gets combined in with the signal is going to cause problems with decoding the data. So while in theory a pure analog waveform is a fantastic way to transmit information, it's really not possible. So when we look at digital is just defining some voltage levels that create ones and zeros. And so sometimes we'll call those symbols. And then you put a whole bunch of symbols together and you get data or words. And so what that allows for is we can put a lot of noise on the signal and we can still recover the original data. And so digital is really an analog waveform, like I said in the video. It's just that it's been encoded with some information. So for printed circuit boards and wires, you'll typically use two levels, 0 and 1, go figure. Now, if you want to get into a really cool modulation scheme, go look up QAM, which is like quadrature amplitude modulation. There's all kinds of modulation schemes, but this will give you an idea of how digital data is sent wirelessly. It's not as simple as just 0 and 1. Okay, let's see. Mark wants to know, how do you choose between a pull-up and pull-down resistor? Is there power savings? Is it just to make the logic easier? So let's first cover the inverted logic. As I mentioned in, I think it's number 15 is the pull-up resistors. If you use a pull-up resistor with a button, then you'll actually be looking for a low when the button is pressed. And I think for some people, that seems like it's inverted logic. And the reality is, that's a human issue, not an engineering issue. The microcontroller, it doesn't care if it's high or low. And so what I actually do in my programs is I create define statements to define when the button is pressed and not pressed. And that way I can look at an if statement, and the if statement will be if button equal pressed, then go do something. And I find that way easier to read and understand than if button equal low, because I don't really know what low means. And so that's just one tip, is maybe use define statements. Now, if you go over my blog on ballengineer.com, I actually have a blog posting where I talk about the difference between define and the constant keyword and why you should, I think I say you should really never use define. Well, here's the one time I usually do use it. Now, in terms of when to select a pull down, about the only time I really use pull downs is like in the case of a MOSFET where I want to keep the gate at a low when a system is first being powered on. Or if I have an IC that I need to pull a signal down to 0. It's not something I typically use with buttons. Part of the reason why is that buttons, I usually use them with microcontrollers. And until the ESP8266, I had never worked with a microcontroller that had built-in pull downs. And so I just, throughout my career, have always used pull-ups, which isn't to say you couldn't. Now, I have heard from a couple of engineers that are way more experienced than I am that one reason to avoid pull downs is for a safety reason. And in a specific situation, like when you have a button and an LED connected over a cable. And so what they've tried to explain to me is that if there's a fault in the cable, it's less likely to create a short if you're using a pull-up versus a pull-down. And to be honest, I haven't really worked it all out to understand why that's the case. They're a lot smarter than I am, so I just did what they said. Another long question, so here's my summary. On the linear regulator video, Donald points out that the part number indicated the output voltage. In the case of the linear regulator video example, I use the LM7805, where the 05 means 5 volts. And so if you had an LM7812, then guess what? The 12 means, well, 12 volts. So I forgot to point that out. Now, in terms of what did I mean by adjustable? So if I showed you an LM317, does that mean that it outputs 17 volts? Well, no, actually, I'm pretty sure it can't. The LM317 is an adjustable regulator. And so the way these work is on the output pin, you put a voltage divider, like we talked about in video number 13, and connect that to a feedback pin on the regulator. And so by using a voltage divider, the regulator will actually be adjustable. And so you could use 2 fixed resistors to select any voltage, or sometimes what you'll see is a potentiometer so that you can actually adjust the output voltage. The really cool thing is the fixed regulators actually sort of already have that circuit built in. Not only that, you can also use a fixed regulator as an adjustable regulator, sort of. And we might cover that later on because I think that's a good way to understand how linear regulators work. Now, in my parts kit, I typically only keep 2 linear regulators, a 7805 or a modern equivalent, and an LM317, or again, a modern equivalent. And that's because with the 7805, I get 5 volts, super common. And with the 317, I can configure for any other voltage. So I don't need to have like 10 different regulators sitting around in my kit. Thanks again, Donald. I really should have pointed that out in the video, and you got me thinking about doing a video on the difference between fixed and adjustable regulators. So Bernhard asks, how do you know how to pick the value of a flyback diode? So in the motor video, when I drew both the discrete transistor and the discrete H-bridge, I threw protection diodes in the circuit, but I didn't mention which diode to use. And so typically, if you're doing like a hobby project or using these small hobby motors, the common diode to use is the 1N4001. Now there's a whole series of these diodes. It starts with a 1, goes up to 7. And so with each one of them, the specs are just a little bit higher and higher. Now, if you want to pick a specific diode, you really only need to know 2 things. What's the voltage of the motor and how much current is flowing through it? And with that, we can start to calculate or pick a diode. Now remember in the video I talked about when the source is turned off, the electromagnetic field creates it basically starts to collapse, generating current. So what that means is whatever energy is used to create the magnetic field, you're going to get roughly the same voltage and current out of it. And so when I'm picking a diode, the first thing I do is figure out the current. So let's say it's 1 volt, 5 amps. And then, So when I'm picking a diode, the first thing I do is look at the motor, which in this case, let's say it's a 5 volt motor that draws 1 amp. So because of that field collapsing and the timing of the collapse, you might end up seeing twice whatever was actually used. And so I immediately double those numbers. So I say 2 amps, 10 volts. And then when I go look for a diode, I double that one more time. And so now I'm up to 4 amps and 5, 10, 20 volts. So I want a diode that is rated for at least 4 amps and 20 volts. The next thing you need to understand is there's a difference between the continuous rating and the pulse rating of a diode. You might also call or hear pulse called surge rating. And so if you think about like the motor's magnetic field collapsing, as it collapses, there's a big surge of energy and then it starts to dissipate very quickly. And so we don't need a diode that's continuously rated for the full motor current because it's not going to see it the whole time. And so for example, if we go and look at the 1N4001, we can see that it's rated for 50 volts, so we're good there, a 30 amp pulse, so we're good there, and 1 amp continuous. Now that one bothers me a little bit because I do like to have a little bit more D-rating. That's why I doubled the number twice, is to D-rate the applied value to the diode, but it's probably still okay. We have a little bit of a meta question coming from John asking if I make all the animations myself. And the answer is, yep, I'm a one-man show. I do the animations, I write the scripts, I shoot, I edit. I do use a little bit of stock content, so a few stock images. Sometimes, especially when I'm talking about people like Jorg Ohm and Ben Franklin, I'll get a public domain image from, say, Wiki Commons with proper attribution. And so I try to use stock content when I can, but for the kind of videos we're doing, that's not much out there. The soundtrack, the background music, like in this video, is basically just what I would call a stock loop that I'm using. The introduction music that I use in the opening video screen, like, you know, this. That one is actually, that was a piece of stock music I found. I applied a couple of audio filters and then I added the modem sound because I really like the way that it sounds when a modem connects. In fact, it's the thing I missed most from the using computers in the 1990s. But anyway, videos generally take about 100 hours. It's about 10 to 15 hours per minute of video that you see. So some of the videos that are 70 or 7 minutes are closer to 100 hours. The motors video is a total exception. I had to learn how to use Blender and then a program called Element 3D, which is a plugin in After Effects. So between those two and then modifying one of the models I found, it ended up taking almost 250 hours, which is why it was almost 6 weeks from the time I said coming soon to when the video was done. When I posted coming soon, I honestly thought I had 2 weeks of work done, and I worked on it almost every day for 6 weeks to finish it. So that one was a lot tougher than I thought. But it's been fun and I like to do them. They have a unique style. I like the way that they look, and so I hope that they're kind of unique in the YouTube tutorial universe. Now, it's also part of why I run the Patreon, because they do take a lot of my time, and I actually end up buying a lot of tools or little pieces of content to make the videos, and so Patreon is there to help offset some of the costs. So the last question actually got asked by a couple of people. I just picked this one, and it's around where did I come up with the name AddOhms? So again, I found this interesting because I had 2 different people ask on back-to-back days on 2 different videos if my name was Adam. And so I realized I never have actually explained where the name AddOhms comes from. In fact, in the first video, I purposely didn't include it because I thought, maybe one day I'll make a behind the scenes video. So the story basically goes, when I was in college, I was a teaching assistant and I was helping students with the 100 level electronics classes. And so just like in the videos, you know, I talk about why you need current limiting resistors, and people would build circuits and always forget these. And so anytime I saw somebody doing working a math problem or solving a circuit or having problems in the lab and they were missing a resistor, I would think I was being clever and say, oh, you forgot to add ohms. which is instead of saying you forgot to add a resistor. I always thought it was really funny. I'm sure my friends got tired of hearing it. I used it all throughout my college career. And in fact, there's probably only 2 people before I created AddOhms that even remembered what I meant by it. And so when I was getting the videos going, I was like, okay, well, I want a name that relates to electronics, and I want something that starts with an A, because when you look at a list, A is always at the top. Well, okay, so that's that's one of my secrets, but so A is always at the top. And so then I remembered I used to say AddOhms, and it works. The really funny thing is when I first showed my logo to a friend, he said, well, I'm not sure I understand. If I look at the logo, I just think it means plus resistors. And I thought, okay, well that works because that's basically the same as AddOhms. So that's where the name comes from. All right, I think that's all the questions I'm gonna answer for now. I wanna thank everybody for asking questions through comments, emails, the AddOhms forums. One of the things I really appreciate with the subscribers that we have to the channel is that we have a very positive community. Most of the questions are positive. Most of the feedback is positive or constructive. And I genuinely appreciate that. There's so much junk on YouTube that to be surrounded by people who are positively thinking, that's a really great feeling. And so with that said, make sure you're subscribed. The brushless motor video is on its way. And again, if I think of any links to go with these questions, I'll add them to addohms.com/QA02. Appreciate everyone's support, and thank you for watching.